All right, so what is the point of this question? Later in the course, we're going to be learning methods. We're going to be learning like this is a method you use for supervised learning. And once you're learning a method, it's very clear what it is, right? This is a method that only works for supervised learning. But in real life, this is maybe sometimes the hardest part. Like how you start, you have some task. What are you going to do? Like which method are you going to use? That is maybe just as important. So this is a little bit of practice with that. And once again, there's the same data set here, and depending on what you do with it, it can either be one thing or another thing. Depending on how you think about it, it will come out to different things. This is like an important thing to know, and also to know the words so you can discuss with other people. I'm taking this data set, I am using it as a supervised learning problem, and I'm doing X, Y, Z, then they'll know what you're talking about. That's why this stuff is important. So in this one, we're sticking with the movie theme, and we have, very similar to what we had last class, we have some information about people, and we have their rating. And they write all this stuff down on a piece of paper, and then we have the pieces of paper. That's our data set. Or you can imagine they're all scanned in a computer. So the first one, use the data who will predict who will enjoy the movie, e.g. for advertising purposes. And what did you guys say? You said it is a supervised learning problem. So 17 to 2, people think it's supervised. I agree, this is a supervised learning problem. So we have the answers. We know what they wrote down. I wrote that they wrote down it's 4 stars or 5 stars. We're going to use their age, gender, and occupation to try to predict what that is. That is a supervised problem because we know the answer is 1 star, 2 star, 3 star, 4 star, or 5 star, and we will go from there. So definitely supervised. This is like a very classical task. This is where we're going to have all those things like the training and the test split and all that stuff, and we're going to learn various different methods. So this is like the most classical type of problem with the most classical type of data set. Now the question is, supervised, unsupervised, we know it's supervised. Is it regression or classification? And this is, again, we came to this discussion last class, even though we didn't use the words regression and classification. Now you've seen the video, and you should sort of know what the difference is, if there's classes or not. What did you guys pick? So 14 to 5 people said classification. Only 5 people said regression. And once again, this is one where I think you could argue it both ways depending on what exactly you're going to do. Once you pick a method, of course, then you're definitely doing one or the other. But I could see both of these being right. There is something in the wording that makes me lean one way or the other way. Does anyone want to say why they picked what they picked?
Normally you don't have 1.5 stars.
Okay.
Yeah.
So you're saying we want to decide if they're doing 1 star, 2 star, 3 star, 4 star, or 5 star.
Yes.
And those are the 5 classes.
Yes.
And that's why you picked classification.
Yes.
Does anybody have a different way to look at it? Yeah.
So here it is saying like who will enjoy, like it does not enjoy or it enjoys. So there are 2 categories.
I see. Okay, so this is the one thing that was in the question is who will enjoy the movie. If it said predict the number of stars, that might be slightly different. You could interpret enjoy the movie as we're just going to predict the stars. But if you are thinking people who enjoy the movie, people who didn't enjoy the movie, that is definitely classification. So if that's where you're thinking and you picked classification, that's a good reason. I will say if you picked classification and you were thinking 1 star, 2 star, 3 star, 4 star, or 5 star as the 5 different classes, the one thing you got to watch out for is in a classification problem, the classes have sort of nothing to do with each other. So in your model, if you tell it these are the 5 classes, 1 star, 2 star, 3 star, 4 star, or 5 star, your model does not know that 5 star is closer to 4 star than 5 star is to 1 star. So if you're thinking 1, 2, 3, 4, 5, then I would probably pick regression. I would say it's a regression problem. You're trying to estimate a number, and that number is between 1 and 5. It's true that the people only inputted things 1, 2, 3, or 4, or 5, but in terms of getting close to the right answer, we should be able to say 4.7, I think is somewhere between 4 and 5, a little bit closer to a 5. And so if you want to think of numbers, those are like continuous quantities, right? Like not discrete quantities, things that can be divided up, and the interval 1 to 5 is totally like that. Then I would pick regression. So if you were thinking 1 to 5 and you picked regression, I think that's great. If you were thinking who will enjoy the movie, enjoy or not enjoy, thinking classification, I think that's also great. I would say if you picked 1 star, 2 star, 3 star, 4 star, or 5 star as your 5 buckets and you pick classification, I would watch out for that. That's like a common thing. And like again, you're leaving some performance on the table because we know that 4 and 5 are closer than 5 and 1. You can bake that into your model by doing a regression. So this is a good one to think about. Any questions or comments about this first one? We're going to move on to the next two in a second. Okay, so that's very similar to what we were talking about last time. The next two are totally different than the last class. So here is one. Use pictures of the paper to create an optical character recognition system. So converting an image, like a JPEG image of the words 5 stars written on a piece of paper, to the number 5. So this is a blank learning problem, and is it classification or regression? Okay, and you guys said, what kind of learning problem did you pick? 12 people picked supervised, 7 people picked unsupervised. And let's see, did we want to do, let's do this as well. Is it classification or regression? 14 to 5 for classification versus regression. So a little bit split here, especially the is it supervised or unsupervised. So 12 to 7 is what, like 60-40 vote? So let me send it back to you. I'll let you guys revote. This time, do discuss with the people near you. Do you think it's unsupervised or supervised, and why do you think it is? Okay, so I'm gonna send this one for a revote. Chat with your neighbors, and we'll revote on this one. You can put in like whatever answer you want, I guess, for the first one, and repeat the same answer you did for the third one. We'll get to that one in a minute. Okay, so go discuss while I copy this. Okay, so there's just over a minute left. Regardless of whether or not you change your mind, you have to put the answer in again. So it should be open now in the same room. Put in your answers again, and we'll see how people change their votes. Okay, like 10 seconds left. There's like a lot of people who still need to hit submit. Again, I'm going to be focusing on the second question here. So if you can kind of breeze through the first and the third and put in your answer for the second, so we can get some see how people change their votes. Okay, there's like 6 or 7 people who still need to get in there. Okay. Okay, let's see what people said this time. So I want to reveal submission counts. All right. What kind of problem? All right. Now it's 11 to 5, supervised to unsupervised. So pretty similar as before. Or last time was it flipped? What was it last time?
12 to 7.
It was 12 to 7. Okay, so the total is slightly different. That's why I'm thrown off. Okay, we said, so 12 to 7, and now it's 11 to 5. So very similar. Not many people change. Does someone want to say why they picked supervised or unsupervised, or why they picked what they picked? Anyone? Yeah.
Yeah. So we thought it was supervised because it says we're converting an image of 5 stars to the number 5. That was an example. So that means we have the output is 5, and we have the input that's 5 stars. So based on that.
Okay, that's very nice. I like that. So you said, I looked at the question here, and it said, in the example, we had to make the output. We had the input. It was some picture that said 5 stars, and we know it had to be the number 5. And because we have the outputs labeled, that makes it supervised. So this is exactly the key thing. If you take your data set and you pay some person to write down, okay, this one is 5, this one is 4, and you make a data set where there's the picture plus whether or not it says, you know, the number that you want, just like in the example, then it is supervised. You could make a case that, you know, I never said that you paid somebody to write down all the numbers, and then you could argue, oh, this is unsupervised. You want to learn without the labels. That would be unsupervised. So if you are thinking we have the true identity of the papers we have, then you should pick supervised. If you're thinking we're trying to do it without knowing the true identities of the paper we have, then you should pick unsupervised. So maybe that's why there was a split. Again, in real life, things are a little ambiguous, right? When we start getting into math questions, there'll be a definite right answer. But for this kind of real life thing, you can kind of always argue both ways. And the important thing is using the words correctly and understanding the ideas. Questions or comments about this supervised versus unsupervised example? Let's see what you think for regression versus classification. This time we're 13 to 3 for classification. This one I would say is unquestionably classification. There is no way that this is regression. And the reason is, it is the categories 1 star, 2 star, 3 star, 4 star, and 5 star, but now we're not thinking of them as numbers anymore, right? Now we're thinking of what digit is it. And now really there is no difference between 5 to 4 versus 5 to 1. They're just two completely different numbers. If somebody writes a 5 and you think that's a 4, that's the same kind of mistake as if somebody writes a 5 and you think it looks like a 1. You've misidentified the digit. You have the wrong digit. So, you know, when you're trying to get the right digits and understand what people wrote, you know, being close doesn't count. Then it really is classes. And you should think about how that is different than when we're interpreting them as numbers in the first case. So I think this one, if you want to think 1 to 5 stars, it's regression. This one, if you think 1 to 5 stars, it's classification, even though they're both 1 to 5 stars, right? So it depends on what you're using them for. Is it going to be classification or regression? Questions or comments about that one? Okay, now the real fun one was the aliens. The aliens, okay, I'm going to go back to the original time you guys answered the question. Assume the people who watched the movie are actually aliens, and they wrote on pieces of paper in a language with symbols that nobody understands. The problem of using the picture of what the aliens wrote to learn something about the alien language is blank learning and a blank problem. And you guys said unsupervised, 17 to 1. This one is unquestionably unsupervised, right? We don't know what the aliens wrote because we don't understand the alien language. I wrote this question a year ago when I was thinking about aliens. Recently, I saw a video of people trying to do this with whales. So they have a microphone and they take the microphone down to the whales and they like listen to the whales who are like making noises at each other. And then they're trying to like analyze it and they're using machine learning models to try to like figure out what the whales are trying to say. But of course, we don't know what the whales are trying to say. It's not like we know what the whales are trying to say and then we're trying to like figure it out, which is like translating other languages. You can ask people, okay, but what did you actually mean when you said these French words? The whales, we don't know. So it's unsupervised. That's for sure because we don't have the labels. Is it a classification or a regression? Very evenly split here. Why don't I send it back one more time? If you think for the aliens, you think it's going to be classification or regression. So ignore all the other blanks. Just do classification or regression. And we'll do it one more time. You can think about what would the classes be? What would the regression be? And we'll do this one quick. So I'll only give you like a minute to think. But let's have a fun revote here about the aliens.
क्या बोलते हैं तो प्रेडिक्ट ही कर सकते हैं क्लासिफाई
करना है ना, तो वही प्रेडिक्ट करना है कि क्या क्लासिफिकेशन
तुम्हें तो पता ही नहीं कि बोल क्या रहे तो तुम क्या प्रेडिक्ट करोगे.
Okay, it's open again. We only have a minute and 30 seconds, so think quickly and then decide. All right, just over 40 seconds left. Okay, 5 seconds left to get your participation mark for this one. All right. Let's see, what did people say? Reveal counts. So, unsupervised learning, and 12 people said classification, 6 people said regression. Does someone want to tell me, if you picked classification, you should be thinking in your mind, these are the classes, right? Or like rough idea, what are the classes going to be? If you picked regression, you should have in your mind, this is the like quantity we're trying to get. Does someone want to tell me either some class ideas or some number ideas? Yeah.
Yeah, because in the previous thing we just said that it was unsupervised, so we're not sure into which category or what is the definite output. So it's like we're just segregating or making clusters of similar looking patterns or something that goes into classification rather than regression.
Got it. Okay, so you're saying, look, we don't even know the symbols. The best we can do is like a group together similar ones, and then our classes will be, there's those guys that are all similar, those guys that are all similar. Those are the classes. I think if you thought that, that's a great answer for classification. And that is kind of what I had in mind as well. For regression, I can come up with some creative ideas for what regression is, Viva. Did anybody think of a quantity you could measure? Yeah.
Like we can see the behavior from the after they say something in your own language, and they behave like a pattern. Then we can see we can say that the piece of information they want to say is more likely the language you want to say in English. Like it will be the percentage.
I see. Okay, percent. This is a really nice thing. So one thing you can measure, the number you can measure, can be a probability of something happening. So for example, you could say, what is the probability after this symbol, the next symbol comes up? So this is one way you can do a lot of things that don't seem like regression. You can turn them into regression problems by asking about probabilities. Another thing you could do is say like, how likely are two different symbols to like go together, right? So like, you have this symbol, it's like a triangle or something, you have this thing that's like a squiggle, you could ask, how likely is it they appear next to each other? And again, you're trying to predict how likely, that's a kind of regression. And in fact, there's a lot of classification problems that you can kind of convert them into regression by saying, what is the likelihood of each of the classes? So the classes, instead of saying it's definitely that class or definitely that class, you say 55% class 1, 45% class 2, and we're trying to predict the probabilities. We're going to get into that very precisely later in the course when we do classification. That's actually why we do regression first, because you learn regression. Once you're an expert at regression, you can use what you know about regression to do classification by probabilities. So really any problem where someone says classification, you say, like, I'm actually going to do regression on the probabilities. So that's definitely one thing. Great discussion. Any other questions or comments to add about this one? Okay, one thing I did want to mention that I think is not really a big deal in the videos, but has become a big deal in real life, is there is another type of learning that's not supervised and it's not unsupervised. It is called self-supervised. So I want to just quickly tell you what supervised learning is. So you know because it is a quote-unquote big deal. Okay, let me tell you. Self-supervised. Okay, and self-supervised learning is when you take an unlabeled data set, so you have a data set with no labels, and you convert it into a supervised learning problem. That is the goal. So we're going to have an unlabeled data set. This is the goal. Unlabeled data set. And we're going to do some magic, and we're going to convert it into a supervised learning problem. So we're going to like create some labels somehow, and we're going to quote unquote create the labels. Okay. And the big advantage of this is unlabeled data is really nice because you can get a lot of unlabeled data for free, right? You remember in the second one I said we have to pay somebody to go through all of the slips of paper and write down is it a 5 or is it a 4, right? So that costs a lot of money. Unlabeled data sets are cheaper. You can get big unlabeled data sets. For example, if you want a big unlabeled data set of English words, you just go download the internet, and then it has a lot of English words on it for free. Unlabeled, great. So that's why we want an unlabeled data set. On the other hand, supervised learning is much better than unsupervised learning. So you can get, there's a lot better techniques, and people understand this very well. That's why we want to do supervised learning. So self-supervised learning is like, we're going to try to do the best of both worlds. We're going to try to take an unlabeled data set, but use the supervised learning, let me say techniques. Okay, so that's the idea. How do we do it? The idea is masking. Masking and unmasking. Mask your data, and predict what is under the mask. Okay, and the most classical example of this is all these large language models like ChatGPT. This is how they are trained. So GPT stands for generalized pre-trained, and it's pre-trained because it is trained on a lot of unlabeled data from the internet using self-supervised learning. After they do this self-supervised learning on this unlabeled data, they do some fine-tuning with some other techniques, but the PT part, pre-trained part, that is all self-supervised learning. And to give you an example, you go to the internet, you download some words, you might find on the internet, you might find this phrase, thou shall not, blah, 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 blah. And what you would do is to train the computer, you would cover up one of the words, you would delete it, and you would ask the computer, please predict after thou shall, please predict the next word. And by doing that, you have taken an unlabeled thing, which is just a string of text with no label, and you have attached a label to it. Thou shalt, and the answer, by the way, is not, right? And now you have a pair of, this is the input, this is the output that I want, and you've done it by taking unlabeled data and masking, covering up parts of it, and asking the computer, please predict the parts that I covered up. So we're taking an unlabeled data set, and we're going to be able to use supervised learning techniques by predicting the things that are missing. And you can use this for words, you could use this for the whales or the aliens, right? You could cover up parts of the thing and try to predict it. You could cover up parts of an image and say, please predict what is behind the blob, right? So like imagine, okay, I don't know, I guess if you, okay, this is a good example. So let's say I have a picture of a bicycle, like this, and I cover up this part of the image, and I say, I'm covering this up. And so the correct answer is a wheel, right? And then I say, Mr. Computer, can you predict when you have a bicycle and you see one wheel in the front, can you predict what is behind it? If your computer program is able to correctly predict that there is a wheel behind the first wheel, now your computer program has understood something about how bicycles behave in the real world, even though we just had images of bikes, right? We didn't tell it bikes have a second wheel behind the first wheel. It kind of learned that on its own through this kind of thing. So this is self-supervised learning, and it's really popular these days because it lets you do all the supervised learning techniques, but on unlabeled data with this masking trick. So I thought I would mention that one as well. Questions or comments about that one? Who's heard of this kind of thing before? Self-supervised learning. Okay, great. I'm going to send some videos around because like you guys should, I think in this day and age, you should have a basic understanding of like how ChatGPT was created and where it came from. Yeah.
Sir, is semi-supervised and self-supervised are the same?
Yeah, this is a great question. Semi-supervised is technically when you do a combination of supervised and unsupervised. Let me write this one down. Supervised. This is a combo of labeled and unlabeled. So a good example would be, imagine in the second example we did. So in the second example we did, so we said we have all these strips of paper and we're going to pay somebody to look at them and tell us what the correct answer is. Does it say 1 or 2 or 3 or 4 or 5? But let's imagine that we have a limited budget, right? So we have like thousands and thousands of pieces of paper, but we only have enough budget to pay for a few hundred pieces of paper to get labeled. A semi-supervised learning would say, let's take our big data set of unlabeled data, along with some small number of labels, and combine all that to do something. So that would be semi-supervised. So for example, we could put them into clusters based on an unsupervised learning algorithm, and then we could use the labels from the supervised one to label the clusters and have something. So that's technically semi-supervised learning. I'll just leave it as it's a combo. So I would say it's different than self-supervised learning. Is like very specifically this idea of you take an unlabeled data set, you create labels by masking things, and then you ask the program to please predict the labels or something like that. So yeah, I'd say they're slightly different. They're related ideas. How can you get more out of your unlabeled set? Yeah, great question. Yeah.
What would reinforcement learning for?
Reinforcement learning is another type of learning where you're not trying to predict something, but you're trying to maximize a value. Let's write this one down too. This is a good one. Okay. And in fact, I teach a whole course on reinforcement learning in the winters. So if you want to know more about reinforcement learning, you can come take my course. Learning. So a good example of this would be you have a robot arm, and you're trying to teach the robot arm to pick up a ball and put it in the bucket. And you say, Mr. Robot Arm, every time you put a ball in the bucket, I give you 1 point. Please maximize the number of points. And reinforcement learning is a system to try to work out with inputs, how can you maximize this idea of putting getting the balls into the bin. One thing that is really common in reinforcement learning is that there's like a connection between the data and what your algorithm is doing, right? So in all of these examples that we did today, you sort of collected all the data and then you're looking at it as the observer. There's no interaction between them. But with the robot arm, there is interaction, right? Because if the robot arm is working really well and knows how to maximize its value, it'll take different actions in the world. Another example is like chess playing programs that are trying to win the game, right? So they get 1 point if they win the game, they get -1 point if they lose the game. And how they play, their understanding of the game affects the rewards they get. So in this one, there's often a feedback loop between the model and the real world. So feedback. So great question. And yeah, this is a kind of a different learning paradigm than the other ones too. We're not going to talk about any reinforcement learning in this course, so you have to take a whole other course if you want to learn about it. Okay, great questions. Anyone else? Okay, let's move on to the next topic. Question number 2. Okay, so this is, again, also from the videos. A supervised learning problem is sometimes phrased as y equals f of x plus epsilon. And actually, this is a regression problem, where now we're talking about numbers. So y and x and epsilon, these are random variables. And I want you to give me a 1-word description of what, in your brain, x, y, and epsilon represent in this problem, in this setup. And again, this is from the videos on supervised versus unsupervised learning. And last but not least, you sometimes see a hat. So something like f hat. So you'll see y equals f of x plus epsilon, and later on in the notes it'll say f hat. And I want you to tell me what you think hat means. The hat means that the quantity with the hat is blank. And again, give me your best sort of one-word explanation for these things. Okay, I did give you guys a warning. There's like 10 seconds left, so put in. Let me bump it up to like 20 seconds, but put in your final guess here of what you think it's going to be, or what your answer is, right? In your own words, what do these things represent? You stretching, or you have a question? Stretching. Okay. Okay, there's still like 8 people who haven't hit submit yet. Hit submit. Okay. Let me, the way you make people answer is you threaten to close it. So let me threaten to close it. I'm going to reveal the answers. You're going to be locked out. Here it comes. Reveal counts. Okay. So, and again, the point of this question, anybody who submits anything is going to get the point for this question. The point is to see what you guys think about it. What did you understand from the reading? And to start a discussion from there. Okay, X. X is one where there are many different names for it. So it's good to know all the names. Let's see how many different names we got. The input, 3 people chose the input. That is how I would think about it as well. The predictors, this is also very common. These are both absolutely correct. The input value, the predict variable. This one, you should be careful because if you say predict variable, you probably mean predictors, the things that are being used to predict. But it's a little ambiguous and it might sound like it's the thing you're trying to predict, which is not X. So just be careful if you say predict variable. I think it's a little under-specified. Independent variable, you'll sometimes hear people say that. This one's less common. Input. Variable. This one is the first one that is definitely wrong. Don't say variable. Everything is a variable. So it doesn't tell you anything. Input. This is the right idea. Input of the function. Inputs. A vector of all the features. Okay, this is another good one to think about that people say is the feature, the vector, or the features. And the point is we have some examples in this learning paradigm of supervised learning. We have examples, and the X is the thing that we're trying to use to predict the other thing. So it's the input or the features, that kind of thing. It is not the output. X is not the output. Okay, there's another wrong one. Okay, very good. I'm trying to think of if there's other names that they sometimes use. I think we got them all. But the right idea is it is the input that is being used to predict the other thing. In the examples we gave, right? So for example, at the movies, X was all this stuff, age, gender, occupation. And so those are the things we're trying to use to predict the other thing. It's the input or the features, right? And for every individual person, these are the features we're trying to use to predict how much they like the movie. Okay. Any questions or comments about X or something to add that I missed? All right, let's move on to Y. What do people say for Y? So if X is the input, then what is Y? The output. Okay, that's a very good one. The outcome, this is less common, but I guess outcome and output are kind of similar. I would stick to output over outcome. Response, this is also another one that comes up a lot. The response variable or the target variable, this is the right idea. The target value, the output. You should be careful. The predicted value makes it sound like it's the thing that I came up with. My prediction is the predicted value. Whereas over here in this equation, Y is not the predicted value. Y is the real actual value that the person wrote down, right? So Y is the actual number of stars the person gave the movie, whereas the predicted value would be like my prediction of what they have. So you got to be careful with that, predicted versus the actual value. Dependent, again, yeah, this sometimes comes up, but less common. Output response variable. Yeah, possible outputs. It's the actual output we got. And it's not the input. Okay, there's one person who has it backwards. Maybe you just press the buttons backwards. Okay, so X and Y, those ones are pretty tame. You've seen those ones your whole life in math classes. This is maybe the new one, this funny Greek letter called epsilon. What is epsilon? Let's find out what people think epsilon is. The error. 11 people think it is the error. And I will tell you right now, it is something to do with error. But if you just say error, there are many sources of error. So if you say error, you will mix up what epsilon is with the other sources of error that we're going to have floating around. So there's many different types of error, and epsilon is something, in this equation, y equals f of x plus epsilon is something very particular to do with error. So I'll send it out for a revote and see if you guys can come up. Maybe you have to go back and read your notes or something. But let's see if we can. 11 people is more than half. And error is not, it's not wrong, but it's not specific enough. So if you typed in error, I would like you to think, what can I say it's more specific than just the error? What type of error is it? Where is it coming from? What is causing this epsilon? So let me send it out for a revote. And if you typed in epsilon, type in something else. Okay, let me repeat it. Okay, it's open again. Let me give you like 2 more minutes. Feel free to chat with people or use your notes to tell me about the epsilon. Okay, 20 seconds left. Put in what you think epsilon is. It's some kind of error, but tell me more specifically, what kind of error is it? Okay, last 5 or 6 people put in some answers. Okay, there we go. You see people learned from the last time when I closed it. Okay, Okay, reveal counts. Okay, x and y, we want epsilon. All right, and now we have 4 people are in this thing, which is 2 words, irreducible error, and that is exactly the right answer. So irreducible error is what they call it in the textbook, and it is this idea of error that cannot be reduced. Even if you are the best possible data science in the whole world, and even if you do things perfectly, and even if you have an infinite amount of data, you will never get rid of this error, because this is the irreducible error. Let me give you an example, which I think is a nice example to illustrate this. And I think this is a very important idea that people don't think enough about, which is the epsilon is the irreducible error. Let me, y equals f of x plus epsilon. This is the irreducible error. Irreducible. Okay, and it's important here that you understand that x and y, these are the real inputs and outputs. They're not our predictions, but the real actual inputs and outputs. This is the output, and this one is the input. Okay, here's my example to tell you what irreducible error is. Let's imagine that x is how many hours you study for a class. How many hours? How many hours you study? And let's imagine y is your grade, your final grade. Final grade. Here's the example. So you're a data scientist. You have a data sample of a bunch of students. You carefully kept track of how many hours they studied. Like you had a little time tracker on their phone and their computer. You know exactly how many minutes they spent studying for the course. And then you, at the end of the course, you get their final grade back. They write the final exam. You know their grade. Okay, that's your data set, x and y. Here's the thing. Even if you have exactly how many hours somebody studied, will you be able to perfectly predict their grade? No. There's other factors that go into it. Like, you know, maybe they took another course. Maybe they took the course already and they already know everything, so they don't need to study a lot. Maybe they're very distracted, so like they study for many hours, but like it doesn't actually help them very much. Maybe they got lucky and there was like a exact problem they studied happened to be on the final exam, right? So the point is, if you have a real data problem, even if you have perfect knowledge of x and y, even if you had billions and billions of kids and you have a huge data set, you would never be able to perfectly predict y given x. And that is always true in every data science problem. You can never actually predict the thing that you want to predict. You will never be able to predict it perfectly. So what is the epsilon, the irreducible error? That represents all other factors outside of our control. All other factors outside of what we know. So we'll never be able to capture with only the information about how many hours somebody studied. There's many other factors. And we bunch all those other things together, all the things that would affect your final grade except for the number of hours you studied, we put that into the epsilon. And that's why it's called the irreducible error, because it's really outside of our control. It's all the stuff that has to do with not x. X is what we know. Epsilon is all the stuff that is not about x. And by making f of x plus epsilon, we make an equation where we have something that represents everything we don't know that we can't access. We can't touch it. We don't know anything about epsilon. So that is why it's called irreducible and why it's important to keep track of. Your job as a data scientist is not to get the perfect answer for y, but to just make the error as small as possible, and you will never get down to 0. There's always going to be this epsilon floating there. In some problems, epsilon is really big, right? If you have a noisy problem, something like this, I don't think you're going to be able to predict the final grades with too much accuracy. Epsilon is pretty big. In other problems, maybe x is the image of the pixels in the image, and y is it a 1 or a 2 or a 3 or a 4 or a 4 or a 5? And in that problem, epsilon is quite small, because we know that humans can look at pieces of paper and figure out what y is very reliably. So in some problems, epsilon is really small. In some problems, epsilon is really big. But it's important to know what it is and to think about it. Questions or comments about the irreducible error? This is, I think, the easiest thing to overlook in those first few videos, is the irreducible error. Let's see what other people said. There's bound to be some other answers. Irreducible error, random error. I think, again, there's all sorts of types of error that we'll see in a minute, and we'll see in the next few classes. A lot of them are random. So random error does not fully specify which type of error it is. Loss function error, I don't think captures it either. We're going to have loss functions and things later. I think that's misleading. It is not a constant, right? It changes. For some people, epsilon is positive. You get a better grade than you should have gotten. For some people, it's negative. You studied a lot, but you accidentally studied the wrong problem. So it's not a constant. It can be big or small. Bias is something very specific that we will go over, and it is not this. So if you said bias, that is wrong, and it has nothing to do with predictions, right? So the epsilon is all about what is going on in reality, right? In reality, there's some relationship between the number of hours you study and your grade, but there's some relationship of other things. And so it's got nothing to do with the predictions. So if you have bias, that is not right. Error that the model can't predict. This is a great answer. This is a great answer. You will never be able to get the epsilon. The epsilon is all the errors that you can't do. Not constant. Estimated error. I think that's not quite right. Probably this person meant to say bias, which is again also wrong. Uncertainty, again, it's a kind of uncertainty, but in a specific way. Is not the bias. So if you said bias, it's not bias. We'll see what bias is soon. And again, it's got something to do with uncertainty, but I wouldn't say it's the degree of uncertainty. All right, great answers. I think we're learning a lot here. Any questions or comments about that? All right, yeah, fantastic work, guys. So let's see. What did people say about the last thing? The hat. What is the hat? The hat. Okay. The first time we did. Okay, I guess I'm in the like copy zone. Here it is. Yeah, the hat. The first time we did the vote, hat was estimated or predicted or estimate. These are all correct. So when you see y equals f of x plus epsilon, the f is the real f in real life that determines the relationship between number of hours and your grade. We cannot ever learn the real f. The best we can do is f hat, which is our prediction of what f should be. There's going to be many quantities that have a hat. So they have something in real life, something that we calculate, and the hat is our estimate, our prediction. So that's what the hats are. A good example would be y hat. Y, remember, was the output. Y hat would be our predicted output. Right? What grade do we think the student will get, given how many hours they work? That would be like a y hat. So very good answer here. Estimated, predicted, estimate. Functions estimated from data. These are all right. So you guys figured that one out. Okay. Okay. So questions or comments about this thing? So this is the paradigm we're going to go deep into of supervised learning, and we're going to start with regression. So everything is a number, and we're really trying to estimate these numbers, right? And we're trying to do the problem of, given this big tables of x's and y's, and this kind of model, y equals f of x plus epsilon, how can we come up with an estimated y hat? Like, how can we estimate what the function f is? There's some real life function f out there in the universe that is connecting how many hours you study and what your final grade is. How can we estimate that function f? And the very first example I'm going to give you guys, that we're going to like really start doing some math, we're going to do a problem where there is no x. There's only epsilon, okay? And when you understand that, we're going to get a good deep dive on what this irreducible error is, and then we're going to bring back the x, and things will make sense. So our first example is y equals f of x plus epsilon, but there is no x, okay? What do I mean by that? Here's the exact problem that we're going to do, and it is about a dice roll. So it is a first example of a regression problem with only a y and no x. So you're trying to estimate the value of y. In real data science problems, you have an x you can work with. In this one, you have no x, okay? And here's the game. It's a game with a 4-sided dice. We're going to label the sides 1, 2, 3, 4. I brought a dice today. It's not a 4-sided dice. It's a 6-sided dice. Let me see. Where's my 6-sided dice? So nice, big, beautiful 6-sided dice. So what we're going to do is every time we see a 5 or a 6, we're going to re-roll it. So you got to pretend it only says 1, 2, 3, 4. Here's the game. You guys get to pick any quantity you want y hat, right? Capital Y is going to be the actual dice roll. So capital Y is going to be the actual dice roll. That's in step 2. So we're going to roll it. I'm going to figure out what capital Y is. You guys get to figure out what is y hat. You get to estimate what you think is going to happen on the dice. Step 3, this is my favorite step. You pay me y minus y hat squared dollars, okay? So if you're off by 2, you owe me $4. If you're off by 3, you owe me $9. I'm going to get rich in step 3. All right, that's the game. So let's do an example of the game. Let's pretend you pick, I don't know, you're like, I think it's going to be a 4. I'm feeling lucky. Let's go. And then we roll. So y hat, you commit to y hat equals 4. I roll the dice. I got a 2. So capital Y was 2. You owe me 4 minus 2 squared equals $4. Okay, great. So you pay me $4. Of course, your job is to make sure not to pay me. You want to make it as small as possible. So the question is for you is, can you figure out the best y hat? And true or false, you can explain why your answer is the best answer. Okay? That's what I want you to do. And this is a real math problem now. So we did some discussion questions that had, you know, maybe this, maybe that. There is an actual, honest to goodness, one best answer you can put in here that is the right best answer. And then there is a mathematical proof. The question is, how comfortable are you? If you know the mathematical proof, put true. If you have no idea, put false. And we're going to do it. I just want to get a sense of what you can do. This is a little bonus. If you find this easy, you can answer this question. The minimum amount of money you will pay me on average. So when you pick the best thing, how much will you pay me? This is a real math problem. If you had a good course in probability, maybe you remember this. If you didn't, then you're going to struggle for a few minutes until I tell you the answer. So let me give you guys like 5 minutes. Feel free to talk to your neighbors. Try to figure out the best number y hat and why it's the best number.
अच्छा 4-sided diagram
So the 3
Okay, I just opened up the thing so you can put your answer in now. If you want to think for a little bit longer, I can extend this. One thing to point out, I think you can enter any number here. So it doesn't have to be an integer, it can be like decimals. And I did say any number you want. So if you want to put in like -7, like fine with me. I'm going to get very rich. This is your choice. Okay, there's like 30 seconds left. First of all, does anybody feel like they would do a lot better with a lot more time? Okay, put in your guesses, and we'll have a discussion. We'll see how close you guys are. I mean, I will show you the answer, so it's okay if you don't know. I'm curious how many people know what the answer is. Okay, and once again, I think I said this somewhere, but if you don't know an answer and you want to just like skip it, just put in like 5, 4, 3, 2, 1 or something like garbage number there, and I'll know that you're just trying to skip it. So that's totally fine. Okay, 15 people have answered. So okay, 16. I'm gonna close it in 1 second. So let's see what we got. Reveal counts. Oh no, that's not what I want. Oh no, reveal counts. Okay, what do people say? The best number y hat is, and people said, 8 people said 3, 5 people said 2.5, 4 people said 2. So is it 3 or 2.5 or 2? Those are the 3 things people picked. All right. Yeah?
Were we working with a 6-sided dice?
It's a 4-sided dice. It's a 4-sided dice. Yes. So this is a 6-sided dice, but I have agreed every time I roll a 5 and a 6, I re-roll it. So it's like those sides don't exist. It's a 4-sided dice. Okay. 3, 2.5, or 2. So let's figure out how to do this. So hopefully you had a course where you did some probability, because the thing you are going to need right now is the knowledge of expected values. Okay. So we defined this thing. You pick y hat, right? And you pay y minus y hat squared dollars. So you can imagine y minus y hat squared, that's how much you pay, but this is a random number, right? If you get it exactly right, then you pay 0. And depending on how y comes out, you pay more or less. So this is a random number that you pay. And of course, when you're making a decision, if something is random and you can't control the randomness, you have no way of predicting my dice roll, right? The best thing you can do is make it on average as small as possible. So I'm going to define, what I'm going to look at is not how much you actually pay, which is random and I can't control it, but the expected value of y minus y hat squared. Okay? And now it's not random. So this is a random number. This is on average how big is the random number. And we want to make that as small as possible. This thing sometimes people call our loss function. So they call this our loss. So they draw a fancy L like that. This stands for loss. And in particular, this is the square loss, because I'm squaring how far away I am. So this is the square loss. Right. And you'll notice the loss depends. It doesn't depend on capital Y. Capital Y got averaged out, right? So it doesn't matter what the dice comes up. The loss function is like on average what happens when you do this. So there's no capital Y, but the loss function does depend on the y hat. So that's why it's called a loss function. It depends on what you chose, on your choice. So if you pick a very good y hat, then you're going to get a big loss. Or sorry, you're going to get a small loss. If you pick a very bad y hat, then you're going to owe me a lot of money, and you're going to have a big loss. Okay, that's why it's called a loss function sometimes. Okay, and we're going to see lots of loss functions in this course. Okay, and in this particular case, it's very simple. There's no data at all. Sometimes the loss function depends on examples and things. In this particular case, it's like the world's simplest example. You have no knowledge of what the dice is going to come up. The only thing you know is that it's a 4-sided dice, and it only depends on whatever you think y hat is. So that you guess y hat, that's why the loss function is there. Okay, let's calculate what this is. So hopefully you saw expected values in your undergrad. To do the expected value, one way is to sum over all the possibilities, multiply by the probabilities, and add them up. So here we're going to use the formula. I think this is sometimes called the law of the unconscious statistician. I have no idea why it's such a weird name, but okay, this is what it is. So we're going to use the expected value of f of x equals the sum over all values x could be, okay, capital X could be, and then you do f of lowercase x times the probability that capital X equals lowercase x. And okay, this is the unconscious statistician. It sounds like I'm making it up, but it's, I promise you it's a real thing. Unconscious statistician. Okay, silly word. So this dice got 4 sides, 4 things it could be. It could be 1 or 2 or 3 or 4. So we're going to have a sum of 4 things. Okay, so it could be y equals 1, and you get 1 minus y hat squared. It could be 2, 2 minus y hat squared. And it could be 3, 3 minus y hat squared. And it could be 4, 4 minus y hat squared. And the law of the unconscious statistician says to do the average, you multiply each of these things by the probability they come up. That is a quarter. It's a fair dice, 1/4 chance for each outcome. So that's the formula. And now it's a function. It's an honest to goodness. I said it was a lost function before. It looked like it had randomness. But now it's an honest to goodness function like you would see in a 10th grade class. Right? You walk into your 10th grade class and say, today we're doing quadratic equations. Here's your function. Bam. Okay? It's an honest function. Let's plot the function and see, just like we were in 10th grade. So I'm going to go to Desmos. This is why I made it a 4-sided dice instead of a 6-sided dice, so there would be less to type in. But here is the function. It's 1/4, 1 minus the input squared, plus 1/4, 2 minus the input squared, plus 1/4, 3 minus the input squared, plus 1/4, 4 minus the input squared. Okay, there we go. Did I type it in correctly? None of you guys are saying I did it wrong, so probably it's right. Okay, so it's a quadratic equation. The loss function, how much you pay me on average, is a quadratic function of y hat. Okay, it's called x here because Desmos thinks of x as the input. It's a quadratic equation. Quadratic equations have a minimum. You're trying to find the minimum of this quadratic equation. Where is the minimum? And this is the answer to the question. Okay, I want to zoom in and find the minimum. The minimum is it 2 or 3 or 2.5? What is it? It's 2.5. That's the minimum. That's the bottom of the quadratic equation. And the height here is 1.25. So the minimum value, the y hat that minimizes how much you pay me is y hat equals 2.5. And how much you pay me when we get there is 1.25. And those are the correct answers to the question that I asked you guys. So over here in this thing, is it this one or this one? The correct answer is 2.5. So if you said 2.5, you got it right. If you said 3 or 2, you are paying me more money than you need to, right? You are paying me, on average, you're going to pay me $1.5. You're going to owe me $1.50 every time, where you could have gotten away with only owing me $1.25 every time. So you're giving me like a free 25 cents of misestimation on your part. That's for 2. For 3, it happens it's symmetric. So you also owe me $1.50. All right. And how much, the minimum amount of money you will pay me is $1.25, 5/4. I wonder if, did anybody get this one right? Let's see. Oh, well, a few people actually did get it right. That's very well. Very good. So if you got this right, then probably you chose true over here. Most people chose false, because it's actually quite tricky to show. But that is one way to see that the real answer is 2.5 and the minimum amount of money is 1.25. You plot it on a computer and you see the answer. Any questions about what we've done so far? All right, here's the thing. 2.5 is a conspicuous number that has something to do with the dice already. All right? So, you know, I put this in the computer and I was like, I don't know what it is, just like chuck it all in there, and then it comes out to 2.5. But if you're a suspicious mathematician person, you might say 2.5, that's a hell of a coincidence. Does anyone know why 2.5 is special for a 4-sided dice? Let's write down the 4-sided dice. So it happens to have a minimum at y hat equals 2.5. And now I claim 2.5 has something to do with y. Okay, so, right? Sort of forget about all this loss function stuff. Just stare at a four-sided dice and the number 2.5. What's the relationship between a four-sided dice that can be either 1 or 2 or 3 or 4? These are the values it can be. It's the mean. It's the mean. So the mean of this number, in fact, again, we could go back to like grade 4 where you learn about averages. What is the average of the numbers 1, 2, 3, 4? It's 2.5. Is this a coincidence, right? We did this whole shebang, we had this whole big thing, and then it turned out the best answer was the mean. The mean. And actually the mean kind of like makes sense. Maybe people, if you guess 2.5 is the right answer, maybe the way you're like, oh, it's somewhere in the middle of the numbers, right? Number line 1, 2, 3, 4, 2.5 right in the middle. That's exactly what the mean does. So is it a coincidence that the mean of the dice was the best value for y hat? And the answer is, of course, no. Not a coincidence. So in fact, here is a, should we say it's a theorem? Let's be fancy. Theorem. The minimum of the loss function y hat equals expected value of y minus y hat squared is always at y hat equals just the average of the random variable y. So in our particular case, y was a four-sided dice, and we calculated this the slow, long way, and we found the minimum was 2.5, but we could have skipped all that if we had known the theorem, which says that the minimum is always at the average value. And here's the proof of the theorem. Here is the proof. So we start with our loss function, L of y hat, which is the expected value of y minus y hat squared. And I'm going to do a mathematician's favorite move, which is you add 0. What is adding 0? Well, it's adding and subtracting the same number. And I'm going to add and subtract y minus expected value of y. Okay, let me do it like this. Plus the expected value of y minus y hat. And all that's all squared. Okay. So I've done nothing, right? We had this thing minus that thing. I subtracted a number, and I added the number. In our example, the number was 2.5, but this is a general proof. It works for whatever random variable y is. If it's a 6-sided dice, it would be 3.5. If it's a 20-sided dice, it would be 10.5. Whatever the average of the random variable capital Y is, I'm adding and subtracting that. Now you're like, well, what's the point of this? This is very silly. You add and subtract something. It doesn't do anything. But now I'm going to split it up into 2 parts. So let's split up into 2 parts. This is part A. And call this capital A. That's a random variable. And this is part B. B is actually not random, right? B is the average of the dice minus whatever number you chose. So it turns out B is not random. But it's some kind of quantity. In this case, it's not random. So I have A plus B all squared. And there is a very famous theorem that you should have learned, again, when you were in like grade 4, not for random numbers, but when you have the sum of 2 things squared. So you have, let me draw it over here in a very suggestive way. If you have A as a vector and you add it over here, and you go B and you go like this at 90 degrees, B, and then you do A plus B squared, that is like doing A plus B is this new vector, C. C. So C is equal to A plus B. Look, I'm adding them together here. And we know if you do the length of C squared, it's the length of A squared plus the length of B squared. That is the Pythagoras theorem. Over here is the Pythagoras theorem for geometry, for triangles. Over here, I'm going to use the Pythagoras theorem for random numbers. So the Pythagoras theorem for random numbers says, let's do a little aside here. Aside. This is Pythagoras for random numbers. And it says the expected value of A plus B squared is equal to the expected value of A squared plus the expected value of B squared. Or in other words, C squared equals A squared plus B squared, but with expected values. The Pythagoras theorem, there is one condition you must check, right? It's not true for every single A and B. They need to have something in particular happen. So let me do a little star, which is terms and conditions, and I will tell you exactly what those are next time. terms and conditions. But for now, please believe me that the Pythagoras theorem applies, and I will explain. Actually, if you can figure out what star is, that's a good exercise. That's your homework. Okay, let's apply it over here. So let's pretend it's true. We have y minus expected value of y squared. That's a squared. So if the Pythagoras theorem works, we get y minus the expected value of y squared plus the expected value over here of the expected value of y minus y hat all squared. So that was b squared and a squared appearing a squared and b squared. Notice b is not random. So there's, taking the expected value of a non-random number is not doing anything. So this is this expected value plus this. This one is just the expected value of y minus y hat squared. This first one has a special name. Does anyone know what this is called? When you see this, you go, aha, that's that. It has a short name, yes.
Mean squared error?
It's related to mean squared error. It's not the mean squared error. It has in like a probability 101 class, this has a one word, the blank of y. What is blank? Let me give some hints. It starts with a V.
Variance?
Variance, yes, okay, good. People knew it right away. Variance. This is the variance of y. So y has some amount of variance, and what we have done by this Pythagoras trick, we have taken the loss function, which was originally some huge nasty thing. When we use the law of the unconscious statistician, it was the sum of a bunch of things. And look, we have factored it into vertex form of the quadratic equation, right? There's a part that is how far away you are from expected value of y, and there's a variance part. For random dice like we did, a 5-sided dice, the variance is 5/4, and the mean is 2.5. 2.5 minus x squared. So we have taken our huge nasty thing and we have factored it so that it is a constant plus how far away you are from the mean of the random variable. And in this point of view, once we have factored it like this, it is completely clear that what value should you pick? You want to make this as small as possible. You should pick x equals 2.5 to make it 0, and then you're only paying this part. Okay, so maybe I'll add that as a quick, therefore, y hat equals expected value of y is the minimum. Okay, so by this factoring, by this little thing over here, this is the only part you have control over. You want to make it as small as possible. You should make it 0. And when you make it 0, y hat equals the expected value of y. So this is a proof of the theorem that the minimum of the loss function in this particular dice rolling case is the average. And I owe you the terms and conditions on Pythagoras. We will use Pythagoras later to do something called the bias variance decomposition. And this is an important thing to understand as well. So this Pythagoras theorem for random variables, I think, is a good one to know. I will let you think if you can figure out what are the terms and conditions. What do A and B have to satisfy for this to be true? And we're going to do it on Monday's class. We'll finish it up. On Monday's class, we're going to do the same problem again, but this time you will have an x. Okay? So there was no x. Next, we're going to do it with an x, and you're going to see the bias variance decomposition. Make sure you go watch all the videos. Those are all due on Monday, and we'll take everything up on Monday. Okay, I'm going to stop there. I'll be around for a few minutes if you want to come ask a question. Or you can always ask on the forums as well.